and share. Which screen should I share? Screen 2, right? If I share that, can you go on Zoom, see what am I sharing? All right. Okay, two. For you, that will name that as perfect. I'll do my best to grade everything and update Canvas before the final. I'm not ready to the exam though, but I'll do my best. It's not. Am I sharing the right? Yep, sorry. Yeah, there's the practice sets. So, all right, thank you. All right, you can come up. What's that? Because I'm just now. Or with my arm. No, exactly.
In 12 minutes, right?
10, 15, yeah, 12 to 15, that would be wonderful.
I will try my best.
Yeah, please, otherwise we're sitting here and we're
I-
eating pizza.
Okay. Okay, hello everyone. The article I chose for the presentation is heat treatment of sunflower protein isolates near isoelectric point. The other is Mudassir Ahmed Malik, and which this article was posted on Food Chemistry in 2019. I will introduce my contents from five aspects: background, methodology, results, conclusion, and critique. So first, uh, background part. It is well known that heating treatment disrupt the secondary and tertiary structure, exposing hydrophobic region, leading to partial unfolding and may followed by aggregation. At the isoelectric point, protein content there is little net charge uh, outside on the protein, so which promoting the aggregation and reducing the solubility of protein. The present study aims to modify the structure of sunflower protein by applying heat near their isoelectric point to enhance their functionality, evaluate the changes in properties under different treatment. So why they chose sunflower protein isolate? There is no clue inside the paper. So I get some insights from website. The main composite of sunflower proteins are 11S globulin and 2S albumin. Uh, Sunflower protein has lower risk of allergy compared to pea protein, and it is rich in essential amino acids like methionine and cysteine. It also has good functionalities. However, it is low in lysine content, so it cannot be considered as complete protein. There are limited market and research about that. What's more, it can also has some off flavor after processing. Yeah, I searched this online. Yeah, out of the article. So the protein isolate was prepared at pH 10.5 and the temperature of 45 degrees Celsius. And the precipitation was done at pH 4.5. For thermal treatment, the protein isolate was made into solution, and after 24 hours of hydration, pH of solution was adjusted to 3.5, 4.5, 5.5 by using HCl or AOH. Then thermal treatment was carried out in water baths at 80 degrees Celsius for 5, 15, and 25 minutes. Yeah, these are methods used to evaluate the changes in different property. Gelation dynamics, the rheometer is used to measure the condition of gel formation and gel strength. What's more, it can also provide information of viscoelastic properties. DSC can determine the denaturation temperature of protein isolate, uh, which gave information of thermal stability. Uh, TGA thermal gravimetric analysis. I think it is maybe is commonly used, but I never heard this before. I read the paper. The paper said it shows the stability of sunflower protein isolate against the temperature rise. So there will be uh, weight loss during heating. So it measures the weight loss and determines the thermal stability of protein. Circular dichroism. Circular dichroism is not. Yeah, to be honest, I never heard this technique before, but for FDIR, I used it last year. So these two techniques are both used to determine the changes in secondary structure. They have different principles. The circular dichroism measures the difference in absorption of left and right circularly polarized light by a chiromolecular. Yeah, but circular dichroism and FDI are both give information of changes in secondary structure. Uh, X-ray diffraction, it gives information of crystallinity of protein isolate. And the intrinsic fluorescence spectroscopy determines the intrinsic fluorescence of sunflower protein isolates, as we covered in class. Tyrosine, phenylalanine, tryptophan can all absorb light around 280 nanometers. So so the spectral we can get the information of changes in tertiary structure through intrinsic fluorescence spectroscopy. The study on viscoelastic properties of sunflower protein gel prepared from treated and untreated isolate were carried out by monitoring the change in storage modulus, uh, which is J prime, loss modulus J double prime, and the loss tangent uh, during heating, holding, and cooling. Uh, from the figure, we can the G prime storage modulus. We can consider it as an indication of uh, elasticity, and for J double prime, it gave information of viscosity. So it was observed that G prime value increased with in temperature for all the protein isolate gels, indicating the formation of stronger gels upon heating. The denaturation and the exposure of hydrophobic groups enhance the protein-protein interaction, which results in stronger gel and was evidenced with increasing in G prime value. Treated protein. Yes, the right corner shows the definition of different letters. So N means native, and others are treated under different treatments. So the treated protein isolates had lower G prime value than gels prepared from native protein isolates. This just the protein isolates near isoelectric points had a lower tendency form to form gel, and the lowest gel strength was obtained at the pH 45, which shows the blue line at the bottom. Yeah, it may contribute to it is attributed to the lower surface charge on protein molecules, which caused the formation of protein aggregate. At pH 3.5 and 5.5, yeah, the protein gel had a higher strength as compared to pH 4.5. The higher surface charge on protein molecular induces electrostatic repulsion between protein molecules, uh, resulting in unfolding of protein molecules. Unfolding of protein molecular reduce the intramolecular interaction. Thermal stability was determined through DST. Denaturation temperature indicates the thermal stability of proteins, and enthalpy indicates the extent of denaturation. From this table, we can get the higher denaturation temperature was observed at pH equals to 5.5. As compared to that at pH 3.5. So it means the heat treatment increased the thermal stability of the protein. The decrease in enthalpy value with increasing in heating time could be correlated with content of ordered structure and increase in proportion of denatured proteins. The denaturation of protein during heating process are partially denatured protein require less energy to denature. The decrease in enthalpy upon heating was also reported for other kind of protein, which was not shown in this slide. Thermogravimetric analysis, and to be honest, I'm not very familiar with this technique. So from the paper, it said the initial weight loss results from the water evaporation, and the middle part means means the disruption of protein structure and the subsequent volatilization. The final part, the third state, was attributed to decomposition of major protein components. This indicates that the figure indicates that at pH 4.5, which was shown in left, the left one, the left one was done at pH equals to 4.5, and the upper right, upper right figure shows the samples. Sample was done at pH uh, page, yes. Mm, Sorry. Oh, sorry. This figure shows the,
Time, right? So one was 5 minutes, B 15,
yes,
and then C
H
5
means
minutes and 4.5.
yes,
But you're not showing the rest of the images.
rest, these are all images.
There's A, B, C, D, E, F, G.
G,
Oh,
H, I.
I see, overlap. Okay.
Wait, why did? So the left one is 3.5.
Hmm.
The right up corner is uh
4.5.
4.5, and the right bottom corner figure shows the 5.5.
Hmm.
Yes. Yes. The
Okay, so you're almost at time.
oh,
You're over time.
okay. So we from the figure we can get. Yeah, we can indicate that at pH 4.5, there is more aggregation of protein molecules as compared to pH 3.5 and 5.5, thus allowing higher thermal stability, increasing heating time and at each pH value further increase the thermal stability, suggesting lower weight loss in preheated protein isolates in response to the temperature. So, circular dichrosm. According to the paper, the two negative bonds at 222 and 208 nanometers are indication of alpha helix content, while beta sheet content appear at 218 nanometer with negative bonds. We can see that we can get the loss in secondary structure was more evident in protein samples heated at pH 3.5 and 5.5. Then protein isolates heated at pH 4.5. The intensity of points at 195, 208, and 22 nanometer corresponding the alpha helix content decreased and the intensity of band around 218 nanometer uh, are responding to the beta sheet content increase, indicating the loss in alpha helix and the increase in beta sheet contents. Uh, X-ray diffraction shows both the heat treatment and pH 3.5 and 5.5 reduce the crystallinity of protein isolate. A loss in crystallinity can be attributed to denaturation of protein molecules that cause the subsequent rearrangement in crystal structure of sunflower protein molecules. Intrinsic fluorescence, we can see a red shift after heat treatment and uh, after heat treatment and different pH values, the heat treatment at each pH values results in a progressive decrease in intrinsic fluorescence intensity. This can be attributed to the fact that the heat treatment of protein isolate increases hydrophobicity and subsequently enhance the intermolecular hydrophobic interaction of exposed tryptophan residues, which results in decreased intrinsic fluorescence intensity. Although I don't know this meaning. From this paragraph, it shows there are tryptophan inside the hydrophobic region. So after treating the heat treatment exposed the hydrophobic region to the outside, so the tryptophan will have more interaction with the solvent and other residues. So that's why the intensity was lowered. Conclusion, the study aimed to modify the structure of protein molecules near the isoelectric point to enhance functionality. Low surface charge on protein molecules cause intramolecular interaction negatively affecting functional properties. Sunflower isolate subjected to heat treatment near the isoelectric point showed the significant structural variation. Protein isolates exhibit greater stability against the heat treatment at pH 4.5 due to low surface charge. Heat treatment led to protein molecules unfolding, significantly improving some functionality. And the thermal stability of protein isolates was higher near the isoelectric points and further enhanced with increased thermal treatment. Although the treatment was controlled among samples and several analyses for protein under different heat treatment were done. But as as I mentioned, in the introduction part, this article aims to detect the heat treatment near isoelectric point to enhance the functionality. But indeed, the results only shows the like gel formation. That's the only part I think about functionalities for forming ability, emulsifiability, they are not measured. And in method part, I said they used FDIR, but there are no results about FDIR. They just said in words that there is some changes in amide one region, which shows the increase in beta sheet formation and decrease in alpha helix, but no figures, no data, and limit there are only limit analysis on gel properties instead of other functionalities, and all in all, they didn't say why they chose sunflower protein isolate. I searched this article online, but I got no clue. To be honest, I found some other articles are both are also about sunflower protein isolate, but they are just yeah, they are in the same area. So I think maybe just a company want to promote their product. That's all.
Thank you. All right, questions? Well, this study is very hard to follow. We
Yes.
talked about that when you showed me.
Yes.
Like, I didn't understand how heating actually enhances stability. What was the temperature that they heated at?
Uh,
So they changed the time and the pH, but what was the temperature of this?
they changed the time of heating.
Yeah, time and pH.
Yeah, temperature is 80 degrees Celsius.
So 80.
Yeah, 80.
Did they show any DSC results other than the table, but did they show the?
No, they don't have. But they said because the heat treatment uh, enhanced the cross-linking of protein. So in this case, it increased the
I'm just surprised they were able to find enthalpy. They were usually when you heat for that long,
yeah.
the protein natures and your enthalpy. This is really high enthalpy. Yeah,
Yes.
yeah. I don't know. It's not you. It's still.
Yeah. In the paper, they just said
Hey, press
uh 4.5.
4.5. So
4.5.
it's the isoelectric point.
Yes.
So at 4.5, the entropy is the highest. This is opposite to theory as far as I'm concerned. Because the protein is most susceptible to denaturation at the isoelectric point. Because you lose charge on the surface.
Yes.
So they are susceptible to unfolding. It's very strange result. I would say.
Yes.
Yeah, it's not you, it's the paper. And then with the circular dichroism, did they actually get percentage change in, or just the figures? So they didn't say what the relative abundance is of each
Sorry?
protein structure. They didn't say that the sheet increased, relative abundance increased by 15%.
No, they just from the figure shows the decrease in alpha helix content and increase in beta sheet
Okay.
formation.
And they said the same for FTIR.
No, they didn't set this for FDI. But they didn't have any data for that.
Okay. Well, what do you guys think?
Yeah, to be honest, this article is
You tell us.
yeah. I think how to say it used a lot of as for me there's I chose 3 papers. You said the third one is the best.
My fault.
Yeah.
Okay.
Yeah, sometimes when you first see a paper, you think, oh yeah, it's good. But when you want to explore more information in this paper, you find a lot of problems.
I
What?
think everybody in this room, with few exceptions. Of course, my paper that Helen presents. So, but there was another one. Enzyme. I think I like. I don't remember yours. Was it? I was the key one. And then yeah, we had some. What did you think about yours? I think it's interesting to what you said, but yeah, there's flaws. Yeah. Okay. All right, well, thank you.
Yeah.
All right, we'll move on. I think we're ordering pizza for everybody. Too large? Too large should be enough. One vegetarian and one non-vegetarian you can choose. Okay. Is there anyone stay after 5? Huh? You want to stay after 5? I think we are. So, yes, I'm sorry, but yeah. You can take pizza to your husband. Oh, no, I mean,
Well, he actually come to H1 and say, no, I come after class. And they say, okay, you have to
go have dinner. Tell him, go have dinner on your own. All right. Was all of this recorded on YouTube? Come. All right.
Well, please lower your expectations with this because this is also not very good paper. It's also hard to follow. I know, but just to let you know, that's not very good either.
Set it in positivity.
Okay. Okay, so hello everyone. Today I will present an article on protein modifications. This is the article that I chose to present. We'll be looking at the conjugation of pea protein isolate with gum arabic, and how this through Maillard reaction, and how this Maillard reaction conjugates can improve the physical and oxidative stability of oil in water emulsions. So just starting with, the basic products. So the pea protein, it's mainly composed of these two subunits that are mostly responsible for their functionality. Pea protein is can have potential to be used in the industry as an ingredient because it does have acceptable nutritional quality, low allergenicity, non-GMO. However, the functionality is inferior and usually limits its utilization in food and beverage applications. And it was the one used in this research was donated by Cargill. The gum arabic is a natural polysaccharide. It's a very big structure, highly branched, and it's very soluble in water, up to 50% weight volume, and is widely used in the food industry as a stabilizer, emulsifier, and thickening agent. So that's one of the reasons why it was chosen for this research, because it's widely used in industry, and it was donated by the TIC gums for this research. Quickly, just to explain how we can have this conjugated formed through Maillard reaction. Basically, we need to incubate these two materials, the pea protein and gum arabic, at a certain condition, certain relative humidity, certain temperature for a certain period of time. So then we can induce the condensation reaction between the carbonyl group and the amine group to form the Schiff base that will go through modifications until we get to the Amadori product, which is the first stable product of the reaction. And that's our target for protein modification. Anything beyond that, it's undesirable, and it can lead to browning or other products that we don't want. So previous studies have shown that these conjugates formed via Maillard reaction showed a greater antioxidant activity, and were responsible to decrease the oxidative rancidity of emulsions. And the authors of this article, they think that the main reason for that is the strong iron binding capacity of pea proteins, and they want to understand how the formation of these conjugates would impact this antioxidant activity of the pea protein against the oxidation of the emulsion. So the objective of this research is to evaluate the structural and functional properties of these conjugates, but with emphasis on the physical and oxidative stabilities of the oil and water emulsions. And the authors, they hypothesized that forming these conjugates with gum arabic could help improve the functionality of pea protein. So with the methodology, we'll start explaining the preparation of the conjugates with pea protein and gum arabic. So first, they start with the mixing the pea protein and gum arabic at 1:4 ratio, 1 protein and 4 gum arabic, adjusted to pH 7, then freeze dried this mixture for 48 hours. Then they take 5 grams of this mixture, and they place on a jar. And then this jar is placed on a desiccator that is being kept at 79% relative humidity, 60 degrees Celsius, and at different times of incubation. 0, the reference, 1, 3, and 5 days. Just a side note here, the 79% relative humidity is really high. It's usually not used this high humidity because this can lead to advanced stages of the Maillard reaction. Usually we target lower relative humidity than that. So then after they prepare these conjugates, they analyze the Amadori compounds formed, the melanoidins formed through UVV's absorption. They also measure the free amine groups. They look at the color. They calculated the BI, which is the Browning index. They look at the SDS page, relative solubility, and the surface morphology through SEM. They also then after that they prepare the emulsions. So with all these samples, they prepare emulsions for all these samples. But first they prepare the emulsifier solution. So for that, they mixed 0.2% of the PPI with the gamma arabic conjugates. They mixed it 0.2% with a buffer, 7 pH 7, and then they centrifuged. Then the supernatant is our emulsifier solution. Then they mixed 2% of corn oil with 98% of this emulsifier solution, blended in a high-speed blender, then pass it through a two-stage homogenizer for 3 times, and then kept this emulsions in ice to minimize oxidation. Then they look at they look at the particle size and zeta potential. Then they chose one of these emulsions to continue with the physical stability of the emulsions, and look at the lipid oxidation through storage time. And the controls were just the PPI alone and the mix of PPI and gamma arabic before incubation. And then I'll talk about the results. So first step was to confirm that the PPI conjugated with the gamma arabic. So for that, they use SDS page and FTIR. So for SDS page, one indicator that this reaction occurred for the author was that soluble aggregates on top of the gel, because it wasn't seen before when they incubated just the P protein. That was one indicator, and another indicator was the fading of strong bands that were seen there around 15 and 28. They were strong before, but after incubating with gamma arabic, it was fading. So they concluded that that's one of the main subunits that were involved in the reaction. They also look at the FTIR, and the appearance of new bands were an indicator that was forming mylar products. Then they also looked at non-specific markers and free amine groups to determine the extent of the glycation, the conjugation. So in the first here of the graph A, we're looking at the UV-vis absorption that was used as a non-specific marker. So the absorption was done at 304. Oh, sorry. 304 and 420. So the 420 was attributed to the formation of brown components, and so then we see like an increase. So if we look at the black lines, that's the absorption at 304, and the red lines are absorption of 420. So after the first day of incubation, we see an increase in both absorption that were attributed to the increase of the browning and the mylar products. And then the second graph, they're showing the browning index on the Y left. That we can see that it increased after 5 days of incubation, but after 1 day, sorry, I thought I had some information, but after 1 day is the same browning index for both incubated and not incubated. But when we look at color, we do see a little difference in color. So the first column here is just the P protein, and the second column with P protein with gamma arabic and different types of incubation. And then the free amine groups, which is this side of the y-axis, we do see a high decrease in the free amine groups. That was 18%. I thought I put it here, but that was 18% decrease in free amine groups after the first day of incubation, while for the pea protein alone, after they incubated for the same time, it was only 4% decrease. They also looked at solubility and surface morphology of these samples. They did see an increase in solubility. However, they measured this solubility using Bradford at 1 milligram per ml of sample. So yeah, well, this is not so anything will be soluble at this concentration. So it's not really relevant for us. And then I also looked at the SEM, scanning electron microscopy. They did see difference throughout the after they incubated for some time. They did see a difference in morphology. However, they attributed that they used these images to corroborate the solubility results. So since the solubility results are not really accurate, that also it's not relevant for us. Then they produced the emulsions. They made emulsions with all of these samples and looked at the particle size. The conjugates that were developed after 1 day of incubation were selected to continue with the stability study because they were the ones that presented the smallest particle size. And particle size for an emulsion is important because it can reduce, smaller particle size can reduce the rate of creaminess, make it like a more clear and more homogeneous emulsion, and reduce the rate of coalescence. Yeah. So they selected the PPI gamma rabic conjugates with 1 day of incubation. So then here they are looking at the physical stability of these emulsions with influence of pH. So they produced the emulsion again, the same way as before, and they adjusted the pH from 2 to 8 of these emulsions. Let it sit for 30 minutes and then measure the particle size and charge of the droplets. So for the particle size, sorry, I thought I had we can see that the PPI particle size. So first, let me just explain what is D32 and D43. D32 and D43 are different ways that we can measure particle size. D32 is more like the surface area of the particle, and D43 is more like the volume and mass. So for PPI alone, we can see that the particle size was much higher than for the mixture and the conjugates. That also impacted on the stability. So we saw phase separation for the emulsions with PPI at acidic pHs. But for the mixture and the conjugates, we basically don't see any difference in particle size. It's really similar. And the author attributes the improvement in the stability of emulsions compared to PPI because of the better amphiphilic balance that was given with the gamma rabic added to the system. And then when we look at the charge, we can see that an increase in magnitude of the droplets for both the conjugates and the mix when the pH was less than 6. And another thing that the author say that is that this increased in stability compared to PPI is because of the steric hindrance provided by the gamma rabic. Then they also looked at the influence of thermal processing. So they make the emulsions, they incubated these emulsions in different temperatures, 25, 37, and 72 degrees Celsius for 24 hours. And they evaluated the particle size and the charge again. We do see that the pea protein alone had a bigger particle size compared to the mixture and the conjugates. However, we also don't see much difference between the particle size between the mixture and the conjugates. We do see a difference in charge. So we can see that which is the black line, the conjugates have are more negatively charged compared to the PPI and the mixture. that can leads to a more stability during thermal processing. And then the ionics, and then they look at the ionic strength, so they make the emulsions again, added different concentrations of salt, so 100, 300, and 500 millimolar, and they look at the particle size and charge again. So we can see that for PPI, after they added 100 millimolar, we saw like a dramatic increase in the particle size, and that we didn't see for the mixture and the PPI and gamma rabic conjugates. But other than that, there's also very little difference between the mixture and the conjugates that we can see for the particle size. But we also saw a difference in the charge. They have the same pattern, but the conjugates have a more negative charge compared to the other ones. And then finally, the oxidative stability. So what you're seeing here is the first graph is the formation of lipid hydroperoxides, which is the first primary oxidation products. And then the second one is the formation of hexanol, which is a secondary oxidation product. Oxidation product. So for the first one, formation of lipid hydroperoxides, we see that the formation increases after 7 days of storage, and the conjugates have a more have a delay in the formation of these hydroperoxides. So the author concludes that the conjugates could delay the development of lipid hydroperoxides compared to pea protein alone and the mixture. And then in the second one, we can also see that the hexanol started to appear after this 7 day of storage, but the conjugates remained below the LOD, the limit of detection even. So they concluded that the conjugates, PPI with gamma rabic conjugates, can remarkably prevent the formation of hexanol on these emulsions. So then some conclusions. The authors say that we saw an enhancement in protein solubility, but this is questionable because the way that they measured is not reliable. They also said that they control the Maillard reactions, also questionable especially because of the way that they measured the free amine groups. I'll mention more later, and they also didn't tell us much difference between the mixture and the conjugate. So we didn't see much difference between the particle size. They didn't really talk much about that. The greater stability against the environmental stress was observed for conjugates. This is questionable too, because we barely see any difference in the particle size. And the difference with that was attributed to the steric hindrance effects of the conjugates. And then they saw an inhibition of the formation of volatile compounds for the PPI conjugates. So some strengths of this work is that they provided some information on the oxidative stability of emulsions that I haven't seen many other articles. However, I don't know if you can use, maybe that can be used as a starting point for further research. And some recommendation is that they develop a purification method to remove the unreacted carbohydrates, because they didn't remove the unreacted carbohydrates were still there, and the protein was like less instead of isolate. They didn't remove. So it was less. The solubility measurement, they used Bradford, but they could have measured the protein content in the supernatant by Caldo or Dumas or other more reliable method and increase the concentration. Also to measure the free amine groups, like I mentioned before. So they used L-leucine as a curve for calibration, and we know that lysine is the amino acid that is more reactive in the Maillard reaction, so they should have used a calibration curve with lysine instead of leucine. And then explore other carbohydrates, maybe some byproducts or some other carbohydrates that doesn't have is not an emulsifier, doesn't have an emulsifier properties as gamma arabic. And then the Maillard-induced glycation is a promising modification technique, but they never mention anything about the scalability or how this could be scalable in the future. So that's it.
All right, questions. I have many. Let's see. All right, Dora, go.
I guess going off of like one of your last points, when they did like the SCS page and like solubility and all their assays, did they do it based on protein content or did they just do it based on weight?
Yeah. Good idea. Good question. Based on solubility based on weight, because it's 1 milligram per ml. But SDS page, I don't know. I will have to check. But yeah, they never really mention what is the protein concentration after they do the glycation. You know, like they never mention that.
Yeah, because like we said, like if they didn't remove the unreacted carbs, like that's like what they're losing it by a quarter, basically.
Yeah.
So yeah, it's 20%. It's
Yeah.
1 to 4, right?
Yeah, 1 to 4. So that would be 20%.
Yeah, that's 25 watts.
Yeah.
Yeah.
Yeah, that's a good question. For SDS, but we'll have to check.
Can you explain why not to use the L-leucine and instead use lysine, or can you explain that again?
It's just yes, it's just because the lysine is the most it doesn't mean that other carbohydrates won't react, react in the Maillard reaction, but the lysine is the most reactive carbohydrate because of the free amine that has on the structure. Yeah.
Does it call out or could you guess what the applications like this would go into? Because I guess like going off of how they prepare emulsion, like they did the high shear, but they also like homogenize it. Like, do you know why? Is it going off of a specific application where homogenization is necessary to prepare the emulsion?
Yeah, that's a good question. They never mention anything about that, but I guess so, because they didn't have to do both, right? Like
Yeah, I
the
would think
harmonization
it's-
and the high shear.
Yeah, I would think it's for like plant-based enough, because like we need the homogenization, but I was just curious if like it calls it out in the paper.
Okay, yeah, that was never mentioned.
Oh, I guess like what food applications could this method be applied to? Cause it's based off like the emulsion preparation, they do high shear and homogenization. Why don't they just do high shear?
Just high shear.
Yeah, it's like, isn't that like the standard for emulsion?
Yeah, but sometimes there's two-stage homogenization, so you do this here so that you can form this emulsion, and then you go to homogenization to make the fraction size even smaller to enhance the stability of the emulsion. So the homogenization step is increase the order process. Okay, because for example, in my previous course, I used that when I share with not the homogenizer, and after that use the ultrasound to decrease the particle size and make more of the stable, increase the stability of it. Because the high shape would do something called coarse emulsion, and then homogenization because it's fine.
Yeah, I guess like, yeah, that's like, it seems like very specific for our application, so I'm just curious, like if they call out like specific.
Did they call out?
No.
Because also the amount of oil they only use 2%, which I feel like is usually like for the mouthfeel of a plant-based beverage, so that's why I also assume similar application.
Yeah, the other thing they don't say, why did they add salt? What was the purpose of measuring the emulsion in salt?
To check the ionic stability, like the stability of the emulsion under ionic variation. Yeah.
But again, if they said the application,
Yeah,
we would have,
yeah.
okay, it's gonna be high salt content.
yeah, they never mentioned
They
that
don't
too.
know.
Yeah.
I mean, the big problem for me is they didn't remove unreactive carbohydrate. Another issue I saw, if you go to slide 10. So the one that didn't have from Arabic, it browned just the same, or
Yeah,
even more.
that's true. That's just, this one is just PPI.
But
And
the absorbance does not reflect that. At the absorbance at 420.
yeah,
Also, if you look at the absorbance values, so
they do start
low.
with the same. Cause that's the PPIs alone, and this is the PI with the gammatic.
What was the black?
The
Where's
black,
show?
the black is
The
300.
glycation. Yeah. The 304 is to measure glycation.
Yeah.
Okay, but anyway, the values
Very low.
very low.
Yeah.
And does not reflect the actual browning, so they
Yeah.
didn't do LAB like we do, for example, to look at the actual browning.
They
Yeah.
tend to calculate the browning index, but they don't show it here. They don't have they don't show a table or anything with the LAT. They just show the browning index. Because to calculate the browning index, they need the LA value.
Yeah, I know, but yeah, it doesn't, it showed as if. Now I'm confused, where is the browning index different for the PPI alone than the conjugate?
So the browning index will be looking at like this two.
These two up,
So like this
there was
one
a
and this
difference,
one.
they saw it.
They started pretty similar.
Yeah, but if we look at the actual color, the images, they're the same color.
Yeah. Yes,
Yeah.
I don't see the relevance of.
I'll tell you, it depends on how they produce. Did they dilute it? It's of course to measure the absorbance at 420, it's very, very dilute. We used to do that in the lab and then we stopped it because the absorbance is too low. In order for you to get an absorbance, you prepare a very dilute solution. Now, I don't know how they did the Brownian index, I have no idea. Yeah, that's one. The other one, solubility, go to the slide 11. Okay, so they saw an improvement, but it's 10 to 15%.
Yeah, I know, so low.
It's
right?
very low, and anything under 20 is not tolerable, you guys, let's just make that very clear. I also at 1%, not, yeah, 0.1%, right?
Yeah,
1
0.1,
milligram.
0.1. 1 milligram per ml.
Yeah, and they're so happy with that.
They even mentioned the conclusion.
Water is finally in this situation. Yes, okay, so that's not good. Let's see, can we go to the zeta potential slide 13? I'm just doing this for educational purposes for you guys. Don't get too taken away by the results that mean nothing really. Okay, so with the zeta potential, have you guys ever measured any protein that had -70? Ever? In the lab? No, the maximum we've seen soy that's maybe 40, maybe 42, right? Well, what is that? And also there is no difference. You know, if you look, you said after pH 6, all
Yeah.
of them the
Yeah.
same.
Yeah.
But they concluded that
Yeah.
there's no negative charge for the glycate.
Well, they concluded with that in the pH below 6. They did mention that, but they didn't mention anything after 6 because it's the same.
And the GOM has a positive charge generally. I think it should be positive charge in the project because you cold on it. I'm surprised that above 4.5 is still showing negative, like for the PPI as well. So
Yeah.
if you point to the PPI, is the PPI that?
Yeah.
Oh, it's that, oh, it is 4.5 is still negative.
Yeah, the isolation point.
Okay. We're gonna watch out, it's not right, can't do that.
Would that also depend on hypothetically like what pH they extracted or they decided to be supposed to add?
Well, they used a commercial product and
Yeah.
we spoke about.
But is they're saying that this is the droplet charge, would it be like the protein, would it be different than the protein charge, just the protein?
Well, the droplet charge is based on what they have on the surface of the oil droplet.
Yeah.
And on the surface of the oil droplet, you
Yeah.
have protein. Yeah.
Yeah.
Yeah, I don't know if gum arabic is negative, it is adding charge to that, I don't know if it's a charge.
It's negatively charged.
Huh?
You said it's negatively charged. I don't know.
Or maybe that's what's adding.
Yeah, because it's 1 to 4 anyway.
But PPI,
Yeah,
come on,
yes.
PPI cannot be negative 70
Yeah.
volts. Yeah. Yeah, I don't know. Also, why would the sample without gum arabic brown, that means there is some carbohydrate is in the sample,
Mm,
that they are even not controlling the residual carbohydrate from
from the
causing
causing, yeah,
glycation.
yeah,
So,
that's true.
okay,
Mm.
last, I think slide 16. All right, so this is for maybe people wanting to work with a Fernanda group. But my understanding, limited understanding of lipid oxidation is when you produce hydroperoxide, they're not stable. They should convert. And it seems like the conjugate, they have the hydroperoxide, which is a primary oxidation product. And then you don't see conversion to hexanol. And then they say that the glycation prevented the conversion of
Mhm. Yeah,
hydroperoxide to hexanol.
yeah.
Through what mechanism?
They're saying, well, they're mentioning that actually. Let me just.
Oh,
it's-
okay, so what's the mechanism that prevents? They already oxidized, so you produce the hydroperoxide.
Yeah.
What did they stop? They stopped the propagation of the reaction from?
Yeah, it was saying it was therefore inferred that the conjugates formed a barrier that prevents the transition metal from interacting with the hydroperoxides rather than being a scavenger to quench free radicals generating during storage. So it made like a barrier to prevent the transition matter from interaction with hydroperoxide.
That's a huge assumption.
Yeah.
That's like a huge, big assumption. I don't know.
I don't, yeah, it makes sense. Is it the steric hindrance that like they keep like emphasizing that like
Yeah.
prevents the?
Steric
I
hindrance
don't know.
that prevents the emulsion to like that gives stability of the emulsion.
Oh, yeah, I don't know.
But hydroperoxides are formed. And hydroperoxide to be formed, they need, if there's metal, oxidation, the first step of the oxidation, unless there is the second stage of the oxidation is impacted by some mechanism, but I think it's an assumption. All right, but
Okay.
these are all questions for you guys not to trust everything you've seen, everybody explain things. You know, you have to always think about the theory, the science, and also application. Who will be buying a glycated product that is 80% the gum arabic?
You might as well just add the gum.
Add the gum, and the gum arabic, actually, they are emulsifiers on their own without the protein.
Oh, viscous. Does it say anything about viscosity?
Mm-mm.
They didn't measure viscosity. Okay, that's another.
Yeah.
Anyway,
That's
well then. Thank you. All right. Guys, did anybody remember what the syllabus says about the +5 points that you can get any day in the semester? Extra credit, nobody remembered that in the syllabus. Well, you get +5 today since you are an attendant. I put it on that sheet. Andressa, so you can give me the sheet. I put the +5. It's in the syllabus. Well, a promise is a promise, although you didn't notice that promise.
This is like any random day, because I may do it for like, if you remember everyone saying.
Ah, yeah, when I know everybody's name, I can walk in and give +5 to whoever is in here. So I kind of like trick you guys so that you can come to lecture. But it seems you were coming without being tricked, so that's fine. All right. So I'm going to share again. Oh, so she's online and Gertrude. That's nice. All right, so I'm gonna share again and hope that there's I don't know what I did. Oh. Oh, I'm still having that. How did you?
Not the screen too, so.
So what do I do? Stop sharing. Close.
Sorry.
Tell me, Vichy, what do I do?
Please, Zoom,
No.
share.
Hmm.
So instead of screen two, you would go to whatever presentation you want. Yes.
Aha. I should remember this trick or give me your number next time I'm like, Vichy, how do well, I can't control other classes. Okay. All right. So what I did is I in your slide, there are gonna be extra slides that I'm not gonna talk about just because of time. I need to finish a little bit in Syria and move into the modification. Is the pizza ordered? All right. Okay. Huh? Okay, very good. All right. So what are the main protein fractions in wheat? Albumin, globulin, no, fractions. Prolamins, huh? Gluten. Oh, we call it glutenins. Okay, so it's like Osborne fractionation. You have albumin, globulins, prolamins, glutenins, and glutenins in some literature they are under prolamins. Okay, what gave prolamin their name? Proline and gluten. Okay. They are high in proline and gluten. What are gluten-forming proteins? Why? Not what. Why are they not soluble neutral and alkaline pH? Between 6 and 9, they are not soluble. You have to increase the pH either much higher or much lower. What makes them not soluble in general? They are low in. What is protein they are? Yeah, they're low in acidic and base amino acid. They're just not, they don't have a lot of charge amino acid. Protein and glutamine, not glutamic acid, they are not charged. Okay. All right, and then what are the gluten forming proteins? Now you can tell me. Gliadins and glutenins. And then what are the forces that stabilizes the gluten network? So there's no gluten in wheat. Don't have that trick question. So what happens is when you put the flour with water and start kneading, you form the gluten. So what stabilizes them? Before disulfide bond. Before hydrogen bonding. So hydrogen, because of that, hydrogen plays a major role in the formation of hydrogen bonds. So what brings them, as you denature this protein by kneading, they come together and actually form more beta sheets, intermolecular beta sheet by hydrogen bonding, and then disulfide. So the sulfide interchange happen, and the some cysteine groups are located strategically at the terminus of the protein. So glutenin, they're already large molecular weight and they form intermolecular disulfide. Gliadin does not form intermolecular disulfide in native state, but when you denature those proteins, the gliadin interacts with the glutenin via disulfide interchange. All right, hydrogen bond and disulfide interchange. There is one more. So the tyrosine oxidation, so you would get tyrosine interaction.
This one, but not first that the first is the disulfide bond, and after that is the because I remember they started with this one,
Oh, the order was
Yeah.
disulfide and then they repeat.
and after the last one was the fact.
The figure, was it the figure that shows that? Which figure then? Here, see here, hydrogen bond, disulfide.
Okay, so it was my fault because I ordered based on this slice. The first slide was the disulfide bond and after. Yeah,
I don't remember where it
this
is.
one, this one is with the disulfide bond, and the next one is the beta sheet.
Oh. Yeah, okay, this is old fashioned. The common understanding is that disulfide bonds stabilize. It does stabilize because it is covalently, but for it to form, the hydrogen bonds happen first. That's why the next slide, build up of beta sheets. Okay. Well, lots of animation. All right. Okay, so to give an example of another cereal that is common, the corn protein, zein, for example, is a protein is the main prolemon in corn, and there is no high molecular weight prolemon. So, or there is very small proportion of the glutenin. So therefore, you don't have that high viscoelasticity in corn. So if you want to make cornbread, it really requires some stabilizers. So alpha-zein is the most abundant, up to 70%. It's really very, very hydrophobic. Yeah, that's what I want to remember here. When we try to form the dough, we have to mix above the glass transition, which is higher for zein compared to gluten proteins. So you can form a viscoelastic protein network at higher temperature than room temperature above the glass transition, and you need a higher moisture content. However, when we bake, the beta sheet formation is not stable. It gets destabilized and you get crumbling. So you lose that elasticity that holds the air during baking.
The same, looking to the
Yeah, so the glutenin fraction. Glutenin fraction or high molecular weight prolemon is low in corn. Zein is a prolemon like gliadin. Gliadin is the main prolemon in wheat, but here zein is the main prolemon. So that's the question here. What happens to the structure? The beta sheet is not maintained over time, so unordered structure and collapse. So rice is the same situation. You don't have high molecular weight prolemon. So if you want to make a gluten-free bread from, this is zein still. If you want to make gluten-free bread, it won't rise as much. So you need stabilizers like the hydropropyl methyl cellulose, which is a hydrocolloid added to enhance the viscoelasticity of the dough. So rice, here I jumped ahead of myself. Rice also is high in low molecular weight prolemon, It doesn't have a high amount of the glutenins. So this, in order for it to kind of form a viscoelastic or a good shaped loaf, people add transglutaminase to enhance polymerization between the amine group of lysine and the carboxyamide group of gluten. So other applications that are in recent using Xeon, so this is from Motif before they shut down business. They worked with a patent where they combined Xeon with another protein, I'm not sure what it is, but it provided a better melting properties and stretching characteristic of an alternative dairy. So that's a patented process that they use. So yeah, have you ever tried plant-based cheese? Do you like it? No. Yeah, I don't know if there is in the market corn protein. Somebody said that, who was in the meeting at AOCS? They said they eat hemp cheese, hemp protein cheese. Were you? No, it wasn't 8:30 morning, so.
It was a question for me, right? You
Yeah,
guys-
yeah.
But I don't remember.
Yeah, so, yeah, he just said that because of hemp protein being insoluble, it forms with curd. Well, he said so. Is that true? I don't know. I never tried. But yeah, I don't think, well, if Xeon is insoluble, but what's happening here, it has good melting characteristic and stretching characteristic. That's what it is. Okay, so let's stop here for cereal. That's should be enough. Huh? Stop sharing again. Oh, okay, good. Thank you. I need to take you everywhere with me. And then need to share my next one. Not this one. Where is it? I don't have it here. Where is my? Oh, scroll down.
Yes.
Oh, there. Okay. Very good, very good. And then. All right, my favorite subject. Save the best for last. Protein modification. That's a lot of what we do in the lab. So far, huh? Yeah, it's under week 13, wasn't it there? It's not there? Week 13? Didn't I not open it? All right, so it's there. Okay. So far, you are experts in proteins, right? Don't dump all the information after this class. That's what everybody does, really. So we learned about protein characteristics that are intrinsic. We learned about how processing can impact the characteristic of the protein, structural, what are the functional properties, and how structure is impacted, it impacts function. So now we want to learn about protein modification here that also impact the native structure of the protein, and with that hope to enhance protein functionality. So, but there is not one shoe that fits all. So you don't want to modify the protein, you cannot modify the protein to make it soluble, gel better, emulsify, texturize. There's not one way that you can do, or one method that you can do that enhance all the protein, convert it to a very magical protein. So we're going to talk about the different ways to modify protein: chemical, enzymatic, some physical, natural reaction like glycation already Andressa introduced that topic. And a little bit about biotechnology. It's not my area, but I will introduce it a little bit. All right, so just a recap how structure impacts function. With modification, we aim to change structure so that we can change function. So if you have a protein, like whey protein, beta-lactoglobulin, it's a globular small protein, very hydrophilic on the surface. What would be its function? A good emulsifier, a good gelling agent, soluble, low functionality. All right, soluble, very good. So that's one. When we denature it.
Yeah.
So now, as it is in its native form without treating it, it is good solubility. What about digestion? Low digestibility when it's globular protein. That's why when I think I mentioned it once in infant formulas, they hydrolyze the whey protein because the infant doesn't have the ability to hydrolyze it because it is globular. The enzymes have a hard time reaching it. But once you denature it a little bit, then you can digest it better. So partially denatured. So what happens with the partially denatured protein? Gels better, emulsifies better, improved digestibility. Okay. Now, what happens when it is fully denatured and highly processed to form large protein aggregates? Low solubility, low digestibility, and reduced overall functionality. Very good. Okay, so, and this happens a lot with plant proteins because plant proteins are already complex. And when we process them to extract them from their complex matrices, we cause denaturation. Thermal treatment in industry is not controlled. You get polymerization, and that's where most functionality is poor. And that's why we need to consider protein modification, where we need to figure out ways to enhance protein characteristics, also protein stability, thermal stability. So even whey protein, I'll give you an example that one industry used to be called the Visco, now it's Agriport. They always come with this question: how do we enhance thermal stability of whey protein so that it's stable over storage in a beverage? So modification of the protein is not only to enhance functionality, but to enhance stability during shelf life. So why do we want to modify the protein? So this is, I like to illustrate with a little bit of animation, simple animation here, where you want the protein to be solid. Okay, because you want to produce a high protein beverage. So especially a beverage that is clear is very popular, high protein beverage, very popular if it's clear among athletes or after an exercise, you want to replenish your protein supply. Clear beverages is one product to go to. Now, especially with plant proteins, you want to form dairy alternatives. So you want to form dairy alternative yogurt, plant-based yogurt. So you want it to form a gel, you want it to hold water. Also, if you want to form cream cheese, especially plant-based cream cheese, you want to have a good emulsification properties. That's one application, but also plant-based mayonnaise, for example. We also want to texturize those plant proteins and to make them behave or form texturized material, fiber structure like meat. So we want a lot from these proteins, especially proteins that are already difficult to work with. So like plant proteins are already very difficult to work with. Why? Because they're large proteins, globular, they form quaternary structure, complex quaternary structure. They have high surface hydrophobicity, whereas whey protein here, alpha beta lactoglobulin, is small in molecular weight, usually form dimers at neutral pH, and it has good surface hydrophilicity, so you have good solubility as kind of a start for any functional properties. Whereas those plant proteins are really hard to work with, so they dislike water most of the time. And you also, when we process, they get denatured, they dislike water even more, and then they form massive aggregates that don't like to interact with water and lose functionality. So therefore, we do protein modification. Can you list the types of protein modification? I think we listed some of them. Enzymatic hydrolysis or enzymatic modification can be enzymatic polymerization or deamidation. What else? Conjugation, so Maillard reaction, we're going to talk about that. So I think we talked about them. So we have chemical modification, physical modification, such as, heating. Yeah, heating is one. Homogenization is another. Ultrasound treatment, a pulse electric field, cold plasma. So these are all physical modification. And then biotechnology, we're going to give a little bit of examples of biotechnology versus selective breeding. You know the difference when we say biotechnology modification versus selective breeding? What is the difference? Okay, tell me what's the difference.
No, I'm scared.
Now you're scared?
Biotechnology is like CRISPR and like physically, not physically, changing these genes of it versus
Yes.
selective breeding is like over time putting out certain characteristics.
Very good. Yes, biotechnology, you change the DNA material. So you encode and change the DNA material for selective changes in characteristics. Whereas selective breeding, you breed for certain traits. So you kind of marry certain varieties together, grow them together to select for a specific trait, and it takes several cycles of breeding cycles. And it's much longer process, obviously. Okay, but whatever we do, we want to improve something, right? So either we improve a specific functionality, we enhance nutritional properties. Let's say we are breeding for higher lysine content. That is one thing that you can improve nutritional quality, enhance, reduce susceptibility to enzymatic hydrolysis, for example, casein, beta casein, they can genetically modify to reduce its potential of being hydrolyzed by the native enzymes in milk. So, or you can make, if you hydrolyze, you can produce bioactive peptide to enhance physiological benefits. Okay. But whatever we do, any technology, we have to make sure it's safe. So we have to make sure that non-toxic material is generated, non-toxic material are used to produce them. So, for example, if you want to do enzymatic modification, the first thing industry asks you, is this enzyme GRAS? Can it be used? So we need to make sure no matter what we do, make sure that we don't have any side effects that would potentially make the product not safe. So I'll briefly go over some chemical modifications. there are limited chemical modifications that are allowed here in the States. So often chemical modification might result in a negative effect. So I'll give you examples which ones are allowed and which ones are not. But with chemical modification, mostly you target physical chemical change. So either you make the protein more carries charge or have a higher net charge, or make the protein more hydrophobic, basically to enhance hydrophilic to hydrophobic balance. So increasing the net charge, I'll give you a couple of examples where we can do that. Or increasing the hydrophobicity, for example, adding a long chain anhydride or hydrocarbons, for example. We can change the size either by hydrolysis or acid or alkaline hydrolysis, or we induce cross-linking, thiolation, adding a thiol group or sulfide group. So obviously these are the functionalities that we target to enhance. So advantages of chemical modification, usually it's simple, applicable in the sense that you can scale in industry. Easy, that means easy to implement and not expensive. But there are lots of disadvantages, potentially lack of specificity and reversible reactions. So they are non-specific and they can be reversible. So you can reverse the action or the action can be reversed. And not all side chains are reactive in a chemical modification. Possible generation of toxic components because of the chemical modification, loss of some essential amino acid. A lot of the reactions involve lysine. So loss of lysine is a big one. And we're talking about this.
What's meaning that not all side chains are reactive?
So meaning like you don't have a functional group, you don't have a sulfide group or an OH group or an additional amine group. Yeah. So acylation, what there is under acylation, there are multiple reactions. One of it is acetylation, another is succinylation in the next slide. So acetylation is basically you take acetic anhydride, and then it reacts to give you at the amino terminus, and then you get an acetylated amino group or amino terminus. So what happens is it blocks a positive charge, a potentially positive charge. By blocking a potentially positive charge, you are indirectly increasing the net negative charge of the protein. So that enhances solubility in some cases, in other cases, enhance emulsification by enhancing hydrophobic to hydrophilic ratio. Succinylation is adding a succinic group, succinic anhydride. So it is a negatively charged group. So when it's added, it reacts mostly at the lysine residue. You add a carboxyl group. Here you are directly increasing the net negative charge by adding a negative charge. Enhancing solubility and also thermal stability, because now you have higher charge on the surface. So the higher the charge on the surface, the better the thermal stability. And that's why I was confused by that paper, because at the isoelectric point, they got better stability. How did that happen? Theory tells you the opposite. The more net charge you have on the surface, the more interaction you have with water, the less the protein is prone to open up. So it has better thermal stability. So the main issue with that is the loss of lysine and reduced digestibility of the protein. So the enzyme will be less active towards that protein when it is chemically modified like that. So these kind of modifications, they might happen in different regions of the world. You can do chemical modification, but here in the US, they are banned. They're not allowed to do these kind of chemical modification. However, we can do modification through inducing disulfide interchange or reducing disulfide. So, of course, in analytical technique, we use a lot of reducing agent, but also in food processing, inducing causing the protein to break disulfide linkages or adding enough reagent to promote disulfide interchange. So some sulfides, they are allowed to be used as processing aids, and they can initiate breakage of disulfide bonds and potentially induce disulfide interchange at particular concentration. So if you think of another acceptable reducing agent is ascorbic acid. So in certain systems, it acts as a reducing agent. In bread, we talked about it, it reduces, and once you have pre-sulfide group, you get an oxidation effect where you get disulfide interchange. So it's used a lot as an additive in flour. Thiolation, this is not allowed here again in the US, but this is a direct modification where you add a thiol group, meaning a 3-sulfide group. So you're enhancing the chances to polymerize and cause disulfide interchange. So acid and alkali reactions, so these are, can be obviously done by acidifying or increasing the pH by adding an alkaline. So these are often used during extraction, and sometimes they are added, an acid or a base is added to enhance solubility and other properties. Sometimes, depending on the acidity and alkalinity, we can convert asparagine or glutamine into aspartic acid and glutamic acid, which can help in enhancing solubility because of the added change. More ionizable groups. However, a high alkalinity, that's why when we try to extract proteins, especially plant proteins, we want to figure out ways to extract them at lower pH. Because high alkalinity is not good for the protein. It can destroy essential amino acids, such as lysine. It can also form non-digestible product like lysoalanine. And also causes oxidation. So if you have components that might get oxidized at high alkalinity, you get oxidation. So the off flavor, off color, protein polymerizing. So it's not a good thing that happens. Glycosylation and phosphorylation are allowed in certain countries to improve the solubility of the protein. And their functionality in general. Some are used to enhance gelation, depending on the protein. You can either enhance solubility or enhance other characteristics, depending on the starting protein. So here we attach covalently a carbohydrate or a phosphate. So glycosylation is different than glycation. When we say glycation, it is due to the Maillard reaction. Glycosylation is a chemical reaction using specific chemicals to attach carbohydrate to a protein. And they occur at specific locations or functional groups. Okay. That's it for chemical modification. So I'll move into enzymatic modification. With enzymatic modification, we can hydrolyze the protein. So during cheese making, the proteins are hydrolyzed during fermentation or aging. where the proteases, endogenous proteases or microbial proteases break down protein to give you the specific flavor. Meat tenderization is very common with papain or bromelain to tenderize meat, break down the protein a little bit. Sometimes if you're starting with a very strong flour, that means the protein is very elastic, causes very elastic gluten to form. If you hydrolyze a little bit, you enhance the viscosity, so you balance the viscoelastic properties. Most commonly we produce protein hydrolysate ingredients in the market. There are a lot of whey protein hydrolysate, soy protein hydrolysate, now pea protein hydrolysate as ingredients with specific functionality. So if you try to go, if you are a CPG company and you're trying to select an ingredient with specific enhanced functionality or enhanced solubility, they go to ADM, they click the 20 or 30 options to select from. And all of these options have been subjected to a specific enzymatic modifications. Glutaminase, we use that, I'll give you an example, to deamidate. So basically it's, there is transglutaminase and there is glutaminase, so they are different. The glutaminase, take the amine group, breaks down the amine group, remove it basically from glutamate, and then forms glutamic acid. Glutamate basically, but glutamic acid at particular pH, you have a charged carboxyl group. Whereas transglutaminase, that is another enzyme that actually causes a covalent bond to occur by also removing an amine group, but causing a covalent reaction between the carboxyamide of glutamine and the amine group of lysine. So when I present research that we use glutaminase, and I talk about enhancing solubility or extractability, people in the audience get confused. And sometimes I get the question, oh, we thought that this enzyme glutaminase causes polymerization and loss of solubility. Glutaminase is different than transglutaminase. All right, so to produce hydrolysate, we often target partial hydrolysis. We don't want to completely hydrolyze the protein. It will lose functionality, it become bitter, sour. You don't want that. Often the target is a low degree of hydrolysis, 3 to 8%, to induce some functionality enhancement, enhance digestibility, potentially promote the formation of peptides that could be bioactive, enhance the charges, because when you break the peptide bond, you release ionizable groups, so you supposedly increase protein-water interaction. And this is, it can happen, reduce allergenicity, but in order to call it a hypoallergenic product, the protein has to be digested more than 90%. You will have to break down most of the peptide bonds. Because there is so much variation in human immunoreactivity to different epitopes on the protein. In order for a product to be hypoallergenic, it has to be very hydrolyzed. That's why mostly infants get those hypoallergenic formula. They cannot, they cry, they don't like it, it's bitter, but they can't say much. So, in order to achieve a specific hydrolysis, specific type of peptides, you really need to control pH, temperature, time, type of enzyme specificity, type of substrate, type of processing to obtain a particular functional or desired tailor-made enhancements in functionality. So it's a very complex. Bioactivity, usually a lot of research has shown that you can release bioactive peptide with very low degree of hydrolysis and still maintain low bitterness. So you can get high bioactivity, low bitterness, and when you hydrolyze more, you can get more bitterness, but you reach a plateau with bioactivity. It's an old research paper that showed this. So in terms of comparison, enzymatic hydrolysis to chemical modification, it has advantage. First of all, there are a lot of enzymes that are GRAS, so generally recognized as safe and can be used as processing aid. And most of the enzymatic reactions are very specific and irreversible. So these are some advantages of enzymatic modification over chemical modification. So control of proteolysis is very important. So you need to control how much you hydrolyze the protein, and you need to control what are you hydrolyzing. So there is the degree of hydrolysis, which is the percentage of peptides broken with respect to the total peptides in a protein. So there is an equation that we use to calculate degree of hydrolysis based on how many peptide bonds are broken, but we need to know a lot about the protein. We need to know how many peptides are in that protein in order for us to determine the degree of hydrolysis. And then we need to select what enzymes we use based on the specificity we want. So, for example, up here, in the furthest lane, you have soy protein isolate. So under reducing conditions, you have the beta-lactoglobulin up here, and you have the acidic and basic subunits, glycine subunits. And then if you use pepsin enzyme, pepsin is very specific to glycine subunits. So here you generate low molecular weight peptide, and then the glycine is gone, beta-conglycine is still there. If you use papain or alkylase, for example, they target beta-lactoglobulin, beta-conglycine here, and you generate low molecular weight peptide, but they don't touch the glycine. However, if you use the same enzymes and you start with a denatured protein, so here we use native soy protein, but when the protein is denatured, you lose that specificity to open up, so they're no longer specific to any peptide and any protein. So type of the enzyme is important. The conditions of the reaction is important, and whether or not the protein is denatured. So there is substrate effect, there's type of enzyme, there are conditions of the reaction. All of these play important role when we're trying to produce hydrolysis. This is a research example that I've probably shown before, where we wanted to hydrolyze I like beta-lactoglobulin. I keep saying it. Beta-conglycine has more bioactive peptides in it than glycine. But instead of fractionating beta-conglycine and go through the purification process, then hydrolyzing with the specific enzyme to generate bioactive peptide, we can start with soy protein isolate with that papain to target beta-conglycine and produce similar activity. In this case, we were looking at antihypertensive activity. So we were able to use specific enzymes to target specific units and look at the antihypertensive activity. So mechanism, theoretically, when we hydrolyze, we say, okay, now we're going to have higher protein solubility, for example, because now we have exposed more ionizable groups. With more charges, we have higher thermostability. We might improve gelation, not always, but depending on the specificity of the enzyme and the type of peptides we release and the length of the polypeptides we release, we can enhance We call these peptides, when gelation is enhanced, we call them gelation promoters. So sometimes the industry, they hydrolyze a teensy bit. You know, labeling is very important in industry, and when the consumer reads soy protein hydrolysate, they freak out. Like, what does that mean, hydrolysate, for the common consumer? So there is a rule of thumb in the industry. They say if DH less than 4%, you don't have to call it hydrolysate. You can put soy protein isolate, but it's actually slightly hydrolyzed to enhance. That's why when you look, let's say at ADM, high viscosity SPI, high gelation SPI, high solubility SPI. So they are all hydrolyzed to a certain extent, very low to enhance different characteristics. But like I said, there is no one modification or one enzymatic treatment that makes the protein magical and everything is improved. So to improve solubility, for example, this was, we did a couple of research in the past, but in order to improve solubility in a targeted manner, we needed to optimize enzymatic conditions. So in order to optimize enzymatic condition, we have to use statistical design, because if you think of combinations, let's say you want to test 4 time points and you want to test 3 pHs and you want to test, I don't know, 5 temperature. Full factorial design was going to be in the 80s, number of experimental units that you will have to do to optimize to do a full factorial design. With RSM, there are different designs that you actually can run anywhere between 18 to 24 experimental units that a design randomizes the combination of the different levels of the different factors you have. And you run your experiment with those fewer number of experimental units. And you produce response surface RSM plots where you generate polynomial equations, and you take the one that has the better fit and the highest significance, and determine under what conditions you get this highest response. Then you use that and you generate whatever the value of X, whatever number of, in this example, you have 3 different factors. So you would calculate those factors, levels, and validate the RSM design by producing a hydrolysate under these conditions that this polynomial equation predicted for you. So saves you time, you don't run a full factorial design. And here's an example of 4 independent variables, 4 variables, 3 levels. You have to have 8 to 1 experimental units, whereas if you do RSM, you do 24 in this case. We did that with hydrolyzing pea protein, and we took a commercial PPI as a starting material, and it was like 10% soluble with very pathetic. We increased it by 6-fold following the response surface methodology design. I did that work in Cargill, unfortunately, and we didn't publish. That we produced a patent, and it's a patent, so I didn't publish the work. All right, purists say that they have a good solubility for their PPI. I know why. Okay. Wow. Huh? Doesn't know why. I know why, because purists and Cargill have joint venture and they use the patent. All right, so Delactose Way, that was another project that we had. I had a graduate student that we got it funded by the Midwest Dairy, and they always look for ways to utilize the byproduct. And this byproduct is the byproduct of protein production, whey protein production through membrane filtration. You get a product that is called delactose whey. So it's actually a byproduct when you remove some lactose from it, but still it has some lactose in it, a lot of lactose left in it, and a little bit of protein, 24% protein. So it's mainly used as feed material. So we said, okay, at this low percent of protein, we don't have much functionality of the protein, but can we enhance the functionality of this looking at emulsification, because then we can add it to meat patties to reduce syneresis of water as well as oil. So we thought, okay, can we amplify the functionality of this delactose whey by optimizing protein hydrolysis using also RSM?
In some case, after the emulsification, after filtration, for example.
Yeah, so you take the delactose whey and you apply
It's
as a
the
byproduct
repeat concentration of the lactose acid.
with everything in it. Yeah, you don't do any purification, you just target the protein, and we use RSM to also optimize using different enzymes. So we had two different RSMs, one with alkylase and one with papain, and we enhanced the emulsification. So here's WPI was our reference, the lactose whey was our control, and we were able to enhance the emulsification capacity, activity, and stability compared to the reference protein. We formed patties, and we looked at the compression force, and the hydrolyzed delactose whey using alkylase enzyme had really good compression force compared to adding WPI to the beef patty. Okay, so we did say theoretically that when you hydrolyze, you expose charges, ionizable group. So you would think that you will enhance solubility. So here, what we did is we produced soy protein isolate in the lab, meaning it was not exposed to thermal treatment. So if you take commercial soy protein isolate and measure its solubility at 5% protein, it would be really not that great. But the one we produced in the lab had almost 90% solubility, so it's pretty good. And we thought, okay, if we hydrolyze it and also treat it like a commercial product, we should enhance solubility. But actually, solubility went down. Why? Think of the theories we learned about.
I don't understand. So you said the commercial sample is not soluble because it is hydrolyzed.
No, the commercial sample that we usually get for SPI, we don't know if it's hydrolyzed, they don't tell us, but it went through processing, homogenization, trypsin inhibition, spray drying, okay, the zinc extraction at the beginning to get the fat out. So it saw a lot of treatment. So it's denatured and it's not very soluble. So, but we wanted to control how we produce the SPI and control its treatment. So we produced it in the lab and hydrolyzed it. We thought that we were going to enhance its solubility, but it went down. Why? So, what do we do usually in the lab when we use enzyme after enzymatic hydrolysis? We denature, we have to denature the enzyme, otherwise it keeps chopping on the protein. So apply thermal treatment. So meaning even if we hydrolyze and then you apply thermal treatment, you're gonna still get aggregation when you heat treat. Those peptides, they're not too small. We don't usually hydrolyze very more than 8% degree of hydrolysis, but with the heat, you are really inducing polymerization through hydrophobic interaction. So it didn't work in this case. The type of enzymes that we were looking at, all of them are endoproteases. So they really chopped that protein, broke it, open it up, exposed hydrophobic interactions. So with heat, we lost solubility.
So the problem is because of the heating?
Yes.
Heating caused making the hydrophobic effect?
Yes, yes, yes.
Would the age inactivation also affect the solubility, like the
So there is no pH treatment that will completely inactivate the enzyme without thermal treatment. So even if you try to do acidic inactivation, yeah, you need less temperature, lower temperature, but you still get. But in this study, we looked at not only an endoprotease, we looked at something we use in the lab that is an exoprotease, where it really chops out in the terminal end, so 1 or 2 amino acids at a time. So we increase the charge by doing so, but we don't break the peptide into smaller or more hydrophobic polypeptides. So the solubility of that, this one is with this protease, was increased quite a bit. I think pH 3, but mostly if you look at pH 7, we got about 8 times better solubility. And in this case, we also inactivate the enzyme, but this enzyme at pH 3 and 75, I think, degrees, we were able to inactivate it and still maintain solubility. For hemp protein is really very insoluble protein, but so when we use this enzyme, all of the enzymatic treatment improved it a little bit because we started with very low solubility. It was a very pathetic protein to be soluble. So all enzymatic treatment enhanced solubility a little bit, but the exoprotease enhanced it the most. What pH? So what we do is we measure solubility at 2 pHs. pH 7 to simulate a neutral beverage, and pH 3.4% simulate acidic beverage. So all of, whether it's 3.4 or 7, all of the enzymatic treatment were better in solubility than the one that was not in there. Because we started with very insoluble protein. So when you break it down, even with endoprotease, you expose more charges because the protein was not really charged. So
Is there a difference between the last guy? The one side that is heavy?
oh no, it's just showing that it can cut from both terminals. Yeah. And you don't have to break it by with trypsin first. You can also break them off without the trypsin. That's what we did. We did without trypsin, with trypsin. Yeah. So in this particular case, we were able to enhance solubility with endoprotease, with exoprotease, but exoprotease gave us better solubility. However, we went ahead and produced a beverage. So, you measure solubility and you think it's going to be better. So we produced a beverage from hemp protein concentrate. Of course, it's not soluble, so it didn't form. If you can see, it was all aggregated. And then it separated, then gelled. So it didn't work. But then trypsin, the endoprotease, formed a good beverage and was stable maybe to week 4, and then it broke. This is the one that was the most soluble with the exoprotease. It formed beverage, but then over storage, it's separated. But when you shake it, it goes back in solution if you shake. And it has very low viscosity, so it's good. That's P. It gelled from the beginning and it was very, very viscous the entire time and also separate. So there is hope for hemp protein here. But I'm here to demonstrate that even when you hydrolyze, you might enhance solubility, but it will over storage will aggregate because the protein is denatured, hydrophobic interactions, hydrophobic groups are exposed. So even peptides with upon heating and storage, you can get aggregates basically. So what happens depending on the product. So if you have a dry powder, like infant formula, you'll get caking. High protein beverage, high protein bar, you get hardened due to the aggregation. So even if it's hydrolyzed, it will harden. There were a lot of studies. Our former colleague Ted Labuza, he passed away 2 years ago. He did a lot of research with hydrolyzed whey protein, and all the bars hardened over time. And then when you prepare beverage, you get this cloudiness, turbidity, gelation over time, even with hydrolyzed protein. So thermal treatment, denaturation, aggregation that cause caking, hardening, or gelation in beverages due to hydrophobic interaction with denatured protein, disulfide. So even if you break them into peptides, sulfide groups are there, so it can reform, interchange, disulfide interchange. And if you have reducing sugar, you form Maillard-induced polymerization, contributing more to the aggregation. So factors that impact this phenomenon in beverage, the pH. So the beverage will behave differently under different pH. What protein we're putting in the beverage, hemp protein or whey protein. What's the ionic strength and protein concentration. Do you know the level of protein that you need to claim? You can claim high protein by FDA. You know what it is? 4.2. 4.2%. In order for you to put a good source of protein on the label, you need 4.2% that is bioavailable. So if you put 5% protein in there and it has PD class of 0.8, then you have 4.2% protein. That's what it means. Has to be bioavailable. If it's only for the beverage, to claim, in general, to claim a good source of protein, 4.2% per 100, 4.2 grams per 100 grams of sodium. Yeah, 4.2 grams per 100 grams of sodium. Doesn't have to be a beverage, and but prefer a high, a good source of protein. So the higher the protein concentration in the beverage, the higher the possibility of forming aggregates and lose stability. So reducing shelf life. When you have lower shelf life, you have economic loss. Thus, we need to investigate different ways to reduce the aggregation. Another way we are working on in the lab is with enzymes is deamination, removing this amine group. And we use it to enhance protein extraction, and it also results in enhanced solubility. And we also work with hemp because hemp is very insoluble and hard to extract. You need pH 11 to extract the protein, which is really alkaline and causes color, off flavor, ruin the protein. So we evaluated the enzyme at a reduced pH, and we were able to get an extraction close to 70% compared to only 8% of the protein extracted at pH 8 without the enzyme. So and the solubility improved about 6-fold. Now, this is the industry problem. So even whey protein that is very, very soluble, they always come, this particular company, Javisco, which is Agripur now, always say, can you enhance whey protein thermal stability? It denatures at low temperature. So when you pasteurize, it's going to be denatured. So although it is soluble, it will stay in solution, but it will aggregate over time. So what happens is your beta-lactoglobulin, you heat it, it will denature and then expose hydrophobic groups and the very active cysteine residue causing disulfide interchange here and hydrophobic interaction. So we get polymerization over time. So even though it stays soluble at the beginning when you form the protein beverage, it will sediment over time. So when they try to produce a neutral beverage, usually it's an opaque beverage, chocolate, orange cream, drinks. But a lot of the beverages is acidic clear beverages, but the pH is really low. So to get to this low pH, proteins are buffers, right? So you keep adding acid to reach that pH, and you need a pH less than 4.6, so pasteurization is done at milder pH than at neutral. So you really don't want to be in that isoelectric point range because the protein is an optimer. And so you want to be under that pH and you want to be able to say it's an acidic, so less than 4.6. But then you keep adding that acid, so you get sourness, acidity. So the not only stability issue, but also sourness because of the protein being a buffer. So the solution, some of the solutions were, okay, hydrolyze the protein. All right, so you have increased solubility, however, flavor bitterness was an issue, and hydrolysates are even better buffers than the proteins because now you have more carboxyl groups, more amine groups. So then when you try to adjust the pH, it buffers very quickly. So you add more acid to reach to that 3.2 or 3.4. Sour, astringent, and stability issue remains. It will sediment over time. So we did work on Maillard-induced glycation, another project that was funded by NDA, Midwest Day, many years ago. So what is, Andres already explained, it's a condensation reaction. The Maillard-induced glycation. So you form, the first stable product is Amadori compound. It's very essential that you stay at the Amadori compound and the reaction does not proceed to advanced stages. Otherwise, you get browning. You know the Maillard reaction. Many stages, the initial, the intermediate, and then the advanced glycation end products are produced. Color of flavor, carcinogens, highly polymerized protein. We don't want all of that. So we really want to limit it to the formation of the Amadori compound. So we don't want all of these poor characteristics, including nutritional loss, lysine is lost, poor digestibility when you form polymers, carcinogen, all of that. We don't want that. That's why it's essential to control the reaction. And what Andresa said, you don't want to have a water activity of 79, a relative humidity of 79%, or 0.79 water. This is way high and superb. If you want to induce Maillard reaction, then it will proceed very well. So what we usually do, we want to ensure that water activity is less than optimal. Heating is not high temperature to denature the protein. and use of polysaccharides rather than glucose or small reducing sugars. And we want to partially glycate so that we don't, every lysine is glycated and there will be, we don't want that excessive glycation that might cause potentially gelation, not enhance solubility. So basically what we do when we glycate, we block a positive charge, so you're increasing the net negative charge. And then the increased net negative charge and the small carbohydrate, relatively small, not very small, will enhance surface hydrophilicity. And then we will have less denaturation, less disulfide interchange because of steric hindrance. And increased solivation, meaning interaction with water. So how does it work? We incubate. This is not done by me. One of my students did that. I didn't do this. And then we incubate in a relative humidity chamber at different, we try to figure out what's the best incubation time. And then after we incubate, so that's what we said about in that paper. They didn't take out the unreacted carbohydrate. We don't want it. We want to produce an isolate again with the glycated, partially glycated protein. So we can, it should have above 80% protein. So we need to remove, we usually use chromatography to remove free unreacted using hydrophobic interaction chromatography. And we confirm at which point we get our protein that is glycated. It has some carbohydrate in it, obviously. And we make sure that at this time point we get the protein and the carbohydrates that are not reacted are coming out in the initial fractions. So that is essential. We look at the loss of amino groups at different time conditions. And then we look at the effect on the structure of the protein. So when we glycate, the denaturation temperature goes up. So in the case of whey protein, it went up about 15 degrees. So we induced thermal stability. And also surface hydrophobicity, it goes up a little bit after heating for 10 minutes and then it plateaus. Whereas whey protein isolate is not glycated, gets denatured and then polymerized. When it gets polymerized, we see a reduced surface hydrophobicity. And we look at the polymerization. This is whey protein control. You see it builds up high molecular weight polymer with more heat treatment, whereas the glycated one does not. We looked at the IR using Raman spectroscopy, and the glycated protein did not change in structure. We had very good rigidity, so it didn't denature with heat. Whereas the whey protein denatured, changed in the spectra at different pHs, whereas the glycated whey protein stayed very rigid in structure.
And may not increase the polymerization.
Huh?
May not cause to increase the polymerization.
No. So glycation reduced the polymerization because of steric hindrance. Again, we made sure it's at the initial stage, only amyloid. It didn't go to the advanced stage where you produce big polymer. Yeah. I think I showed it, but very quickly.
Yeah.
Yeah, we look at the percent loss at different time points, and then we select the time point that we got partial kind of blockage. All right, so we did a lot more to understand the structure of that, and then we looked at solubility. Of course, when we do solubility without storage, whey protein is soluble. So we didn't do storage, it's just 100% soluble and it remained soluble when we glycate. But the most important discovery was we don't have to go to pH 3.4. We can formulate at pH 4.5. It's still acidic. You can still do the mild pasteurization. The regular whey protein denatures when you heat it, right? Remember, it falls, if you heat it, it denatures. So at isoelectric point, it's going to fall out of solution. But the glycated protein remained 9% soluble at the isoelectric point. So that was great. We can formulate a beverage at 4.5, and we did. You pasteurize it like it's an acidic beverage, and then it stays soluble. So, and if we need less acid, so it won't be sour or astringent. So that's kind of like the whole goal is to make it acidic beverage, but it's not too acidic, it's not 3.4, so it won't be acidic or sour or beverage. We also did a sensitive study with beverage. It was great, but what is the problem? That this could be not. It was great research. We published the work, everybody was happy except the Visco because scalability. Nobody wants to use this excessive process. We're still working on this. We didn't give up. We tested it with pea protein. We made the pea protein 100% soluble, like whey. But the process is not scalable so far. That's Andres' PhD project. Make it scalable, please. You want to? Yeah, okay. So we've been at it for 12 years.
We want to get.
Oh yeah, go get pizza and come back. We're almost done. Go get pizza. What time is it? 5:30 after that. No, it's not so bad. We're almost done, John. I'm telling you stories now. By this time.
What about you then?
I will easily doesn't have that. Huh? You have an idea? Okay, let's hear it. Huh?
Because I was thinking, you know how you have the soluble aggregates of the P that we still have yet to explore. I was wondering if that was going to diminish if we scaled up. But since I can't put the issue with the development, would it be possible to like mimic a scale up to see if things to have some aggregates by like doing the benchmark regular? Sorry, I just like thought of
Oh,
that.
yeah.
For my little offshoot side project of like how heating the P extraction created the soluble aggregates, like the question was that can also happen with the scaling.
Oh, yeah.
I was thinking about doing like a mimicking the pilot plant of just like heating it, yeah, to see if the heating would, yeah. To further that.
Yes, that's good.
Idea.
Let's talk about it during our meetings.
Yeah.
The straight yard, when I bought. The bottom view, the park, yeah, was not good. But then I fixed it, but we didn't use it. Let's use it.
Okay, yeah, because I was like, oh, I don't think anyone's like actually really used it, but I've seen other people use it,
Yeah.
so.
Yeah,
Yeah, I can bring that up in meetings.
Yes,
I just
yes.
thought about that.
that's cool. What's that?
Race? What is the weather at?
I'll be 45 days out.
So. But that was good.
Or they said they're those for that hour and a half. I'm so antsy. I want to find out.
I hope there's a little capacity.
About this house.
No. Doing. These pictures of the mall haircut, I have like a. when I have my voice. I'm going to do that, and then. Yeah, you actually put a dose in everything for it. It has a very easy to move on, so we can probably use that. I'm not sure if we want to go. I was thinking, but I don't know if they have. I mean, I guess. It's one. You're also like cooking cookies, so just, yeah. Yeah, okay. So we didn't source as the last. Yes. Yeah, we got there without. That's, yeah, I'm not the words they can. Okay. So I think.
I know she's telling you that you guys don't look at it. Huh? Me? I need to finish it. And I'm like, no. No, you can't. It's okay. It's not too bad. You said down eat while I tell you stories. We must. Yeah, that's good. No, do not, you know, some people that then. And then four minutes or so, it was none of them. That's what we're gonna find out, it's not like. I don't know what. No, but that, and then there was this last night. Yeah. Yeah, so we will have this. Very much to. I told them, can I have it? They said. Okay. I will go. Six. Yeah. Everybody has. And are you gonna bend when we tell them? Have you ever been for me? You did for the fish? How long the fish doing? They're fighting. We didn't lose any of them.
Oh, they're happy in their home.
I don't understand why we got behind this fish.
I thought they would get bigger, but.
No, they just stay that big. Alright. So I'll continue with my stories from all these stories of how we modified proteins. So with linking structure to function. So don't get too stressed, we'll be done soon. All right, so this is an example of physical modification called plasma. So it is used in industry, it can be scaled, it's actually used for surface modification in material processing, it is safe, it is energy conservative. And also, it's been investigated for pasteurization, non-thermal pasteurization. And I actually, with this project, I worked with someone from mechanical engineering who said if we can scale it, then it can be doable. We submitted a USDA grant to test scalability, it will get funded. So, I gave up on that project, now I'll put another project in, and now the whole federal government is not funding grants anymore. So there, I think I'm not lucky with it. Anyway, we have not heard yet though. I don't know if we will ever hear. It's been since September. Yeah. Anyway, so this is cool because like I said, it's scalable, it can be it is safe. And just to introduce what whole plasma is, it's the fourth state of matter. So we have solid, liquid, gas, and then plasma, which is ionized gas. And with cold plasma, we can use different sources of gases, air, argon, oxygen, CO2. The work we did, we mostly used argon and oxygen, but depending on the geometry, there are different geometries as well. Sometimes we use air and argon. So either oxygen and argon combination or air and argon, and then there are different geometries that we can have to generate the cold plasma. And what it is, they call it cold plasma, but the temperature is like 50-ish degrees, not really cold, or room temperature is a little above room temperature, but still, it's not high heat. And depending on the geometry and the air or the source of gas, we generate some things we call reactive species. So ozone, for example, is a reactive species, OH radical, oxygen radicals, electrons. So these, the ones that have mostly oxygen and peroxides and ozone, they're called oxygen reactive species. But we also have nitrogen reactive species. So when we generate these species, some of them are long-acting, short-acting species, or long-lived and short-lived species. But mostly, the most common reaction that happens is oxidation. So when we have protein, we promote disulfide enrichment. So also the plasma, subjecting the protein to plasma and a little bit of heat causes unfolding. And with unfolding and oxidation, we get polymerization. But also sometimes, depending on the power, we can get bond cleavage, peptide cleavage as well. So the protein opens up and then induce disulfide linkages through oxidation. We tried different sources of plasma, 3 different types, 3 different temperatures, and 3 different times. And we did that with pea protein, and we looked at the unfolding through looking at the enthalpy of denaturation. So every treatment resulted in unfolding of the protein, with, of course, the more exposure, the more is the unfolding. So the 3 different cold plasma geometries we use is the plasma jet. George has plasma jet in his lab, but we did that at mechanical engineering. They built for us a unit for dielectric barrier discharge, and also another unit for nanosecond pulse discharge. So they are very different geometries, but in all of them we use argon and air, or argon and oxygen. So here we looked at what happened, the oxidation polymerization. So we produced insoluble and soluble aggregates, but some of the treatments caused also bond cleavage. But regardless of the treatment and the time, we saw enhancement in gelation property. We formed stronger gels. Like if you look at the commercial pea protein isolate, it's pathetic. It doesn't gel. Now the ones that we buy for some reason from a different source, the gel's a little better. But this one was really poor in strength. And then we produced our control, which is, we call it native P protein isolate. So it gelled, but not that great. But that control, that protein isolate that we produced, we subjected it to the different treatments. And all the treatments resulted in enhancement in gelation and also in emulsification capacity, ability to hold oil. So we looked at we formed an emulsion, we formed a coarse emulsion and then a fine emulsion by double two-stage homogenization, and we stored the emulsion under accelerated storage conditions for 10 days. So the commercial P, the emulsion formed aggregate, this is CLSM, by the way, confocal light scattering microscopy, where we stain the protein green and the oil red. So you can see that the commercial protein aggregated, whereas all the other emulsions that where the protein was subjected to coplasma form continued no change. So we had regular emulsion throughout storage. Another modification that we did is inducing a polymerization to enhance gelation. So cold plasma enhanced gelation by forming soluble aggregates. So now we try to polymerize the protein, control the polymerization using transglutaminase. We saw also an enhancement in gelation of P protein using transglutaminase. So here we looked at transglutaminase under different conditions, and all of them produced a large molecular weight soluble aggregates. So under reducing conditions, you still see the soluble aggregates because these were not disulfide interchange, these were covalent by transglutaminase reaction. In this study, we looked at pancreas protein, and we did cold plasma treatment and transglutaminase, and we texturized. So here, the texturization properties enhanced for both cold plasma and transglutaminase. So actually, pancreas protein did not form after texturization, did not expand. But these guys expanded, and when we did SEM, scanning electron microscopy, we saw fiber formation. So we always correlate gelation to fiber formation. So we want to enhance gelation through formation of soluble aggregates, and these soluble aggregates behave better for texturization. So among the last I lied. Couple of other last things. So breeding. We said biotechnology and selective breeding. So in this example, we show how we try to find differences in the protein profile among different breeding lines. So here is camelina, and we try to look at how the camelina protein differed. So the breeders gave us a lot. This is just a sample, gave us a lot, like maybe 50 different lines, and we screened them, and we selected 4 lines or 5 lines, and we asked the breeders to plant them again the next season so that we have enough to produce isolates and determine how these different lines vary in functionality. So we produce a lot of trait data so that the breeders can go back and continue their selective breeding cycle. Now, in biotechnology, we said it's different than genetic engineering. We are modifying the genetic material for targeted changes. So what's happening in this picture? I don't really know if this is true, but there is the mama, and this is actually a puppy.
Not a cat.
It's a cat, but genetically modified. So the mother had a cat. I don't know if this is true, but I think it's very dramatic to show you that you can change genetic material. See? Hold it off and.
Do we do a sample breeding, so like it's faster, or is it not?
No, it's not, no, you cannot, well, you can, but it still takes a cycle, so. They call it like first parents, first generations, so. It's like every year they have to kind of take the daughter or the sibling. Or not the child. What do they call them? F1 and F3, right? Is that what they call it?
Generational.
Yeah, national, but they call it family one, offspring. Yeah, and then it's process. Yeah. We had one time Steve Multi came and gave a talk in seminar, that how the total classmates explain the meaning of people. And those are the rain of last year, maybe that's a year now. It was great time, it's an environment. I cannot repeat what he said, but it takes a long time to select, to do selective breeding. Whereas genetic engineering, we just change the genetic material. And usually you target, okay, I'm going to change the genetic material, the coding, so I have more lysine in my protein. Or do specific enhancement in charged amino acids so that I enhance solubility. Or cause potentially peptides, sequences that would have physiological contribution. This never worked. I mean, no matter how many years I hear about the use of other humans, you will still variable with protein. You can remove an epitope like 10% of the people react to, but you might generate new epitopes that another 10% of people will react to. So it's just there. People attempt it, but it doesn't never work.
Classified as a,
Huh?
the gene for that is classified as a modification.
GMO, yeah.
That's it.
Yeah, but GMOs are not always GMO is targeting the protein. For example, soy.
I know, but for the protein, when protein modified by technology,
It's called GM. Yeah, the genetically modified. You are not using breeding and many the plants to produce. You are actually changing, encoding the sequence. Yeah. So yeah. So how it works? You get the DNA material. And then design the change, you have a hypothesis and design the change in the DNA to promote the specific change in your protein. It's not as simple as that, but you know, you have your hypothesis, you design the change, and then you put the DNA material, the new DNA material, and produce the protein. To test the hypothesis, we normally use that in using microorganisms. So that you generate a little bit of that protein and evaluate the bigger hypotheses first. So first do that. And you get a small amount of protein and you can do testing like microscale spectrometry to determine the gel strength of that protein. Yeah. And see if it works, then you do it on larger scale. Applications where they actually change the protein, changing gluten to make it stronger, gluten forming proteins, deletion of plasmid sites, so the beta casein is susceptible to the endogenous plasmid proteins, changing the site so that it's no longer susceptible, increasing the glycosylation of the beta casein is the least glycosylated, if you remember from the dairy protein lecture, so you can increase the glycosylation and make it less hydrophobic. But a more practical example is a perfect day. They have a non-dairy milk. So the way they produce that non-dairy milk is they get yeast cells and they inject or put in those yeast cells cow DNA to produce the whey protein and the casein protein. And then they formulate with similar amount of lactose and fat and not necessarily fat, non-dairy fat, and produce milk. Has anybody had this? No, I didn't. Another genetic modification is producing meat in peas. Piggy soy. So they're actually producing, yeah, I mean, it's not on scale, it's just experimental. But yeah, you can change the DNA to produce meat protein in the seeds. Yeah. So you glycated proteins or hydrolysate, what happens? Better solubility, depending on how much glycation and how long is your chain, you can actually enhance gelation. Some say that emulsification is enhanced. We never really focused on emulsion or gelation. We always attempt partial glycation to enhance solubility. Do we improve thermal stability? Yeah, why? How? Remember? Huh?
Moisture flavors.
Moisture in here, but also the higher net charge of the protein raises the denaturation temperature because you have more charge on the surface of protein, so it resists denaturation and reacts more with water. Does it have reduced or improved digestibility? You think? We didn't talk about that. It depends. So we tested with whey protein, actually digestibility enhanced 9% by just enzymatic hydrolysis digestion that we did. That for pea protein, we did that, digestibility did not change at all. And then people think, do you think we use lysine? Do you expect to use lysine? Yes, we are blocking, but do we degrade it? If we stop at the amidori compound, the lysine is not degraded. So when the action propagates to advanced stages, the lysine becomes a different component and it loses biological availability. However, when we ingest the protein, we have enzymes, not only proteases, we have glucosidases enzymes that actually can break the covalent link between a sugar and a protein. And if the lysine is not degraded, it will be still available. So we did measure lysine content in the glycated protein and in the reference protein, and the lysine content is different. Because when we measure amino acid, we hydrolyze with acid, so all the covalent bonds are broken, so the lysine content didn't actually change. But if glycation is severe and it's not controlled, like in the case of that paper that showed browning, yes, so it's not just blocked, it is degraded. What about hydrolyzed protein? Potentially, maybe. It's not always the case, depending on the types of peptides that are released. Sometimes it can be anything. You can enhance these functionality or make them worse. For example, if you break the proteins to very, very small peptides, you lose anosmia. Because then they won't have enough hydrophobic to hydrophilic balance to go to the interface. So depending on the type of peptide, the degree of hydrolysis, and the length of the peptide, you may or may not enhance any of these characteristics. So that's why hydrolysis is tricky. It has to be tailored, controlled to the specific functionality that you're looking for. I'm done. Okay, you can't say that I took 2 hours. You cannot say that because there was a break. How long was it?
5 minutes. Huh?
The presentations took an hour and.
Yeah, the presentation took an hour. I started like 4. Yes.
30.
What?
The lecture started around 4:30.
Yeah, see, or no, I won't say 4:30, I think 4:50. And then we had 10 minutes break, so just like half an hour of your time extra. Psychological, I'm working on your psychology. Only half an hour extra is what I took from you. All right, you guys. Thank you.
Thank you. Yeah.
Wow.
Where is?
Oh,
What?
it's like
No, it's like.
different
Down.
fractions.